Hello, once again. So today we're going to be kind of looking at some Maxwell relations and applying those Maxwell relations to try and solve for the change in temperature once again. That's kind of the common theme that's going around right now with these homework problems, right? So, namely, we have this particular setup where we have some metal sample. And as it stands right now, this sample of metal, or a solid rather, not necessarily a metal, but a solid, is being exerted on by some high pressures, really high pressure environment. That's what we have going on here, right? Now, what we're going to do is that we're going to take our pressure and we're going to slowly increment it little by little by little, more and more and more, such that we can consider that the change in pressure is some sort of quasi-static process, right? So if we know that it's underneath an immense amount of pressure and we want to know, and we know that we're increasing the pressure a little bit by little bit, we want to solve what our final temperature is, but we want to do it in terms of our change in pressure, our absolute temperature, our molar specific heat, our density, and then our volume coefficient of expansion alpha, right? So, where do we start? Well, if you need to know really anything about any sort of relationship, we can fall back onto the laws of thermodynamics and start from some variable describing a change of states, right? And one way we can do that is by using the state function of entropy. Now, what we do is that we just let entropy be, in this case, a function of both pressure and of temperature, right? And when we do when we allow it to be a function like this, we can use the definition of the differential of entropy ds, and where we can write out our different changes of entropy with respect to our other variables' pressures, and that with temperature as well. We can do this for any other variable. You can do energy and volume, temperature, volume, doesn't matter. You can use entropy for this kind of setup. Or something like Helmholtz free energy, or Gibbs even, except you do need to use the variables that are pertinent with those instead of just entropy in general, right? Okay, so with that in mind, we can actually begin to make some substitutions, knowing some known quantities that we've already encountered before. Namely, we have our specific heat with constant pressure, Cp, and we know that that's equal times the temperature times the change of entropy with respect to temperature at some constant value of pressure, right? We also know that our change in pressure, our change of entropy with respect to pressure at constant temperature is equal to the negative change in volume with respect to temperature at a constant pressure as well. We get that from the Maxwell relations, for which we can, I think it's given to you in Rife. I can't think of them off the top of my head, so that's a gap in my knowledge I need to fill, so I can go in the test and, not have to worry about thinking about it, just knowing it, Anyway, with these substitutions in mind, we can algebraically move this t over to the left-hand side and then make some simple substitutions, and we can write entropy in a new way. And we write entropy in this new way being ds is equal to the heat capacity with constant pressure divided by the temperature times an incremental change in temperature minus the change in volume with respect to temperature to constant pressure times that small change in constant pressure. Now, we also know that our value of the coefficient of the expansion of the volume alpha is equal to the inverse of the volume times the change of the volume with respect to the temperature, T, right? So once again, we do some more algebraic manipulation, we substitute that in, and our expression for entropy becomes this, where we have a value of our specific heat with a constant pressure P divided by the temperature times dt minus V times alpha, because you move this guy from the denominator over here to the numerator over here, times our small change in temperature dP, right? Now, because we're told that this particular process is quasi-static, we can know that our change in entropy is going to be about 0 anyway. So if we just go on ahead and let the change in entropy of our system be 0, right, we can just set this whole term equal to 0, and then algebraically solve for delta t. Now, once we do that, we need to note something here. We do have the overall specific heat at constant pressure, C sub P, but we need it in terms of the density and the molar specific heat, right? So I went and I did some Googling on Wikipedia, and I was able to piece together some handy dandy little relation tying our molar specific heat to our regular specific heat at a constant pressure, and namely that our specific heat at a constant pressure is equal to the molar specific heat at a constant pressure times the density, rho, times the volume. So what we do is that we can just substitute that value into our expression for delta T, cancel out the values for V, and then we obtain our final expression for a change in temperature of a solid sample that is already underneath some high amount of pressure and having its pressure being incrementally changed. So yeah, that's just one use of the Maxwell relations that we can use to calculate some variables that we need to know for some sort of experimental setup, and it really demonstrates how we can have some sort of really a non-physical quantity related to an actual physical quantity, and then tying those things together and using them in real life to describe and make predictions about how materials behave underneath different, I guess, variables, different conditions. Couldn't think of that for a moment there. But yeah, anyway, that's that problem. Yeah.